Hi there. Today we are going to learn plotting diagrams for shear force and bending moment for simply supported beam. Well, let's consider the example. As I have just mentioned, let's consider a single span simply supported beam. We know that simply supported beam has two types of supports. It's pinned support and rolled support. The beam has a span which equals 9 meters. The beam is subjected to loads. There are two types of loads. The first type of load is applied on the beam is a force, or point load as it's also known. The force is equal to 6 kilonewtons. Mark the force as capital F. The second type of load is applied on the beam is uniformly distributed load. The uniformly distributed load of magnitude 4 kilonewtons per meters is distributed over the beam. The applied loads divide the beam into regions of different distances. These are 1.5 meters, 2.5 meters, 3 meters, and 2 meters. It's like any other analysis of a structure. The analysis of beam must begin with support reaction determination. To begin with, let's mark supports. The left pinned support is marked as a capital A, and right rolled support as a capital B. Next, grade the design model. To do this, we discard the supports and show support reactions instead. At point A, the support reaction RA is applied instead of the pinned support. There is no horizontal component of support reaction at point A, because there are no horizontal loads, and at point B, the support reaction RB is applied instead of the roller support. To support reactions determination is used equilibrium equations, which describe the static equilibrium of all internal and external forces of the system. To begin with, let's consider moment equilibrium about point A. For the equilibrium equation, it's necessary to determine the resultant force of a uniformly distributed load. For a uniformly distributed load, the resultant force is the area of the rectangle with sides which equal to the load magnitude and the distance where the force is applied. The resultant force is applied at the intersection of the diagonals of the rectangle. Let's write down the formula and determine the resultant force. As we can see, the resultant force is 12 kilonewtons. Now, we can write an equilibrium equation for the moments about point A. Pay attention to the signs. Bear in mind, if the force is clockwise, the sign is plus. And if the force is counterclockwise, the sign is minus. The moment equation consists of the support reaction at point B with the minus sign, the resultant force of a uniformly distributed load with the plus sign, and the point force with the plus sign. From this equation, you can get a formula for calculating the support reaction at point B. Now, let's put the numerical value into this formula to get the value of the support reaction. When we solve this formula, we get that support reaction at point B is equal to 8.3 kilonewtons. Let's show this on the design model. Now, let's determine the support reaction at point A. In this case, the equilibrium equation for the shear force is used. Let's write this equation. As we can see, this is an equation with one unknown value. This is value of the support reaction at point A. So, we can easily determine its value. Let's write down and solve the formula for the support reaction at point A. We got that the support reaction at point A is 9.7 kilonewtons. Now, to continue, we divide the beam into regions by imaginary cross-sections. The cross-sections are drawn in a manner that they divide the beam at the spots where the force is applied, as well as at the border between the loaded and unloaded parts of the beam. So, there are 4 regions formed by 3 sections. Let's show and write sequentially them so we don't forget. Now consider each of these regions in turn. Let's start by plotting the shear force diagram. For shear force determination, the equilibrium equation for shear forces is used. We are going to consider the first region. It's region A1. Let's cut off the beam on the right side of the point A, as close as possible to point A. Therefore, we can see shear force at point A is equal to the support reaction RA. Let's write it down and put the value on the diagram. Now we successively apply the same technique to determine the shear force in other spots. Cut the beam as close as we can on the left side of section 1. In this case, as in the previous one, the shear force is equal to the support reaction at point A. Great! We got a value of shear force that occurs along with region A1. Plot it on the diagram. Now, consider the region 1, 2. When we cut off the right side of the beam as close as possible to section 1 to the right, we will see that now the force is added in the equilibrium equation. We got the shear force is equal to 3 and 7 kilonewtons. There is no more external load along the region 1, 2, from the first section to the second section. So, the shear force to the left of section 2 is also 3 and 7 kilonewtons. Show it on the diagram. Next, consider the region between section 2 and 3. Know that a uniformly distributed load is applied along this region, and as we previously determined, the resultant force of the uniformly distributed load is applied in the middle of this region. In addition, we know that the resultant force of the uniformly distributed load is calculated as a product of the load magnitude and the length of the load. Since we are defining the shearing force as close as possible to section number 2 to the right, that is, the length of the load trends to 0. Therefore, the resultant force between section number 2 and the current point is also equal to 0. That's why, in this case, the shearing force is the same as to the left side from the section, that is 3 and 7 kilonewtons. Consider a spot as close as possible to section 3 to the left. In this case, the resultant force of the uniformly distributed load has to be taken into consideration in the equilibrium equation. Write and solve the equilibrium equation for the shear force. Solving the equation, we get the shear force equal to minus 8 and 3 kilonewtons. Put this ordinate on the diagram and link it with the continuous line with the previous ordinate in section number 2. As you can see, this line intersects the baseline of the diagram, that is, where the shear force is 0. We also see that the sign of the shear force changes the sign of plus to minus, but this is of no fundamental importance. Consider region 3B. Since there are no more external loads in the region between section 3 and point B, the shear force in section 3 on the right and at point B is minus 8 and 3 kilonewtons. Well, We have plotted the shear force diagram. Now let's start plotting the bending moment diagram. Consider region A1. Since there is a hinge at point A, we can immediately determine there are no bending moments here, because no bending moments can occur in hinges. This also applies to support B. There is no bending moment there are also. But in section number 1, there is already B a certain bending moment. Let's define it using the equilibrium equation for bending moments. Let me remind you that the bending moment in the cross-section is defined as the product of the force and the distance from the section to the force. Let's write this equation, and then determine the value of the bending moment in cross-section number 1. Solving the equation, we get the bending moment is 14 and 6 kN-meters. Putting on the diagram, we must remember that the bending moment in the diagram is shown from the side of the stretched fibers. In our case, the stretched fibers are at the bottom of the beam. Next, we determine the value of the bending moment in section number 2. Let's write down and analyze the equilibrium equation of the left part of the beam in section 2. In the equation, there is a bending moment from the support direction and force F. The bending moment from the support direction is the product of the support direction at the distance between point A and section number 2. This moment has a plus sign because its direction is clockwise around section number 2. The moment from the force F is the product of the force F and the distance between the spot of force application and section number 2. This moment has a minus sign because its direction is counterclockwise around section number 2. The required distances are easy to determine because they are known. It's enough to add the individual lengths of the beam regions. Solving the equation, we determine that the moment is equal to 23 and 8 kN-meters. Put it on the diagram and link it with a line with the previous ordinate. Little by little, the diagram of the bending moment appears. But we should be careful, because the most important region of the beam is region 2-3. Because there, firstly, a uniformly distributed load is applied, and secondly, the sign of the shear force changes along this region. And, as you know, at the point where the diagram of the shear force crosses the baseline, there is a maximum bending moment. Thus, it's not enough to determine the value of the bending moment at point 2 and 3. It's also necessary to determine the value of bending moment at the point where the shear force is 0. It should also be noted that the diagram of the bending moment from a uniformly distributed load is a curved. In particular, it's a square parabola. So, mark the spot where the diagram of the shear force crosses the baseline as a capital C on the design model. To begin with, there is a need to determine the coordinate of point C. Mark the coordinate of point C as the small letter x on the design model. Let's find out it. To this, the triangle similarity is used. Consider the part of the shear force diagram between section 2 and 3, that is where point C is located. On the design model, this part of the shear force diagram is colored in red. If we modify this diagram, we get a right-angled triangle to which the triangle similarity applies. One leg is the sum of the absolute ordinates of the diagram, and the other leg is the length of the region of the diagram. Comparing the legs of the triangle, we get the desired value x. It's 0 and 925 meters. But that's not all. We must find also the resultant force W with a single quiet of a part of the uniformly distributed load along the length x. It's the product of the length x and the magnitude of the uniformly distributed load. It's 3 and 7 kilonewtons. Now we can write and solve the equilibrium equation for bending moments around point C. It's 25 and 5 kilonewton meters. Let's plot this value on the diagram. Now we have to determine only the value of the bending moment in section 3. Let me remind you that at point B, as we have already found out, the bending moment is 0. So, for this we write and solve the equation. This time we must consider all external loads. Solving the equation, we get that the bending moment is 16 and 9 kilonewton meters. Let's finish plotting the diagram. Let me remind you once again that on region 2-3, the diagram of bending moments has the form of a square parabola. So, the task is done. Thank you for watching. Be so kind, like and subscribe to the channel.